right, welcome back to our machine design series. Today we're talking about mechanical springs. So first, let's start with a definition as usual. A spring is a machine component that is intentionally more compliant than other parts in a load-bearing path. Okay, so we spent a good amount of time when we were talking about shafts discussing how to prevent the shaft from undergoing too much deflection. Because remember, too much deflection would cause potentially mating gear teeth to become out of alignment. It could do damage to bearings that are supporting the shaft. And so we said we want to limit the amount of deflection that a shaft can experience during service. With a spring, our goal is a bit different. Springs are typically used intentionally to take up a lot of deflection or to experience a lot of deflection, right? So at this point in class, I typically ask students to look around and try to find some different springs. They're used in our everyday lives all the time. And the most often first thing that students will find is a compression spring. So these are the springs that exist inside of your ballpoint pen. They experience compression. That's the deflection that they're designed to provide. So they're designed to absorb energy when you push down on them, compress them. Okay, then the next spring that you might find pretty easily somewhere around you would be a torsion spring. So if you're wearing a hair clip, you'll find a torsion spring on that clip. They're also used commonly in clipboards, anything that's designed to twist and provide some resistance to that twisting moment. So a torsion spring typically looks something like this, where we are providing some kind of twisting moment that the spring is resisting. So that's a torsion spring. And then extension spring, there are some various small parts that use extension springs. For example, I have a ring camera set up at home that has an extension spring to allow it to move in rotate in different ways, extend. The most common place you'll find these at home might be your garage door, or these are also the springs that are used on trampolines. So they'll typically have an end, one coil of the spring that's been pried away to be able to grab on to something and allow it to be pulled in tension. So these springs are providing either let me use my laser. So these springs are providing a push or a pull or a twist. in order to store or absorb energy. And to determine how much of a push or a pull these springs are going to exhibit, we measure something called the spring rate. Which is denoted with a lowercase letter k. And this is the slope of the load deflection curve. So you may also hear this spring rate called the spring constant. It's also the basis for Hooke's law. So Hooke's law for compression or extension springs can look like this. K equals F divided by Y, where this is our spring constant, here's the force that's being applied to the spring, and Y is the deflection. So if I want to know what my spring rate is, and I have some spring, I need to measure it, I can put it in either tensile test setup or a compression test setup, measure the force, measure the deflection, and then take those two data sets, divide them, and that will give me my slope. Or really what you would do is take the slope of the force versus displacement curve, that average slope you would use for K. Okay, but for torsion springs, we need to measure something different, right? Because for torsion springs, we're not just applying a force, we're applying a moment. And so the load deflection curve for a torsion spring is going to be that applied moment divided by the angular deflection theta. Okay, and these spring rates, they may be constant if they're linear springs. They can also vary if you have a nonlinear spring. For the purposes of our class, we will focus on linear springs, but just keep in mind that K does not always have to be linear. With high deflections especially, K can start to change. Okay, next let's talk about what happens when we combine springs. So springs can be combined in series or parallel. And depending on how we combine them, the force and deflection relationship will change. So when combined in series, let's draw first what it looks like. I want to move all of this actually to the next page. Okay, so in series, we have one spring here. We'll just draw two springs for now. These are compression springs. So I provide a force on either side that is compressing these two springs. They have constants K1 and K2. Now, when these springs are combined in series, the same force is passing through both of these springs. So each spring is contributing to the total deflection. And so to find the total spring constant that is a combination of these two, we take 1 over K1, we add 1 over K2, and then we invert that to find the total equivalent spring rate. Another way to think about this is that we have two springs in series, and so we can't have a combined spring stiffness that is greater than either individual component. The weaker spring will deflect. Okay, and then in parallel, we'll do again 2 compression springs sandwiched together between these 2 plates. Again, we're providing a force that is compressing these springs on either side. But now, since they're combined in parallel, all these springs, which these 2 springs, K1 and K2, are going to have the same deflection. So the force is splitting between these individual springs. And so to find the total spring rate for these 2 springs, we simply add them together. Okay, and this is just for these 2 examples, but we can extend this to say in general, for springs in series, 1 over K total is equal to 1 over K1 plus 1 over K2 plus however many springs you have all the way to Kn. Okay, so the pattern continues. Same thing for springs in parallel. Our total spring stiffness is K1 plus K2 plus however many springs we have up until Kn. Okay, so those are the general forms of the equations to find the combined spring rate for springs either in series or in parallel. All right, so let's just do a quick example. And then we'll wrap up this video. So if I have spring 1 that has a spring rate of 10 pounds per inch, and I combine that in series with another spring, K2, that has a stiffness of 15 pounds per inch, and I'm going to apply a force of 50 pounds in compression on either side. The question is, what is the total deflection of these 2 springs in parallel? Okay, so the easiest way, I think, to approach this is to take these 2 springs and combine them together so that we have an equivalent system that is 1 spring, K total, and that is being compressed by this 50-pound force. Okay, because in this scenario, now I can just directly apply Hooke's law, F equals Kx, or F equals Ky, and I can solve for y, total deflection. So let's combine our spring stiffnesses to find K total. 1 over K total is equal to 1 over K1, which is 10 pounds per inch, plus 1 over K2, which is 15 pounds per inch. So if I plug this into my calculator, let's see, 1 over 10 plus 1 over 15, and then I've got to invert that. All right, you should get 6. And again, this makes sense. When we have 2 springs in series, our total spring stiffness should never be greater than either of the individual spring stiffness components or spring rate components. So 6 pounds per inch is less than both 10 and 15 pounds per inch. So it makes sense. And now all we have left to do is, that's not our final answer. We need to solve for the deflection using Hooke's law. So I have F, which is 50 pounds. I have K, which is 6 pounds per inch. And I can solve for the Y deflection. So 50 divided by 6 is going to give me 8.33 inches. Okay, so that is our total deflection of the springs. You could also try to break this down into the individual spring deflection components, and then add the deflection of each individual spring together, and that would give you the same final answer. So I encourage you to try that on your own and make sure that that's what you get. And in the meantime, thank you for watching this video, and I hope to see you in the next one, where we will start talking about the geometry and get more into the specifics of helical compression springs. So see you then.